The nervous system, they work together. Okay? The endocrine system and the nervous system, they work together. That is the reason we call it neuroendocrine system. Neuroendocrine system. So the endocrine system and the nervous system, they work together. We call it neuroendocrine system. Okay. Now, what does the endocrine system do? The endocrine system produces hormones, right? The endocrine system produces hormones. So hormones are released. Once they're released, they travel in the bloodstream, or they act on the neighboring cell, or they act on themselves. Okay? And what does the nervous system do? The nervous system produces nerve impulses, right? Nerve impulses. Now, these nerve impulses, they can act on the endocrine system. Remember, the endocrine system affects the nervous system affects the endocrine system, okay? So we can say in a way they work together, okay? They work together. Now, in case of endocrine system, what does exactly endocrine system do? Endocrine system, one of the most important things that it affects the metabolism. Okay, it alters the metabolism. So one of its most important effects is on metabolism, body metabolism. It can regulate the growth, development, and also reproductive processes. And this is we will see this later on. And what does the nervous system do? Nervous system can stimulate or inhibit the production of hormones. Okay, so it affects the production of the hormones, or sometimes it inhibits the production of hormones. Now, also hormones can affect the nerve impulses. Now, when we talk about the general functions of hormones, we can say hormones affect everything which are there in our body. Okay, for example, it can regulate the extracellular fluid, metabolism, biological contraction of cardiac and smooth muscle, granular secretions, some immune functions, growth and development, reproduction. I can say everything in our body is controlled by hormones. Okay, so hormones are very, very important for our body. Also, their amount is very important, how much hormones are produced in our body. Now, when we talk about the production of hormones, the secretions, okay, when we discuss about the endocrine glands, okay, they can be either exocrine glands or endocrine glands. So there are two types of glands, exocrine glands and endocrine glands. When we talk about exocrine glands, that means their secretions, okay, they are released in a cavity. So the secretions are released in a cavity, For example, all the gastrointestinal hormones which are produced, where are they released? They're released in the stomach, right? Or also, we can say, for example, sweat, the glands, they're exocrine glands, okay? Now, in case of endocrine glands, the hormones are produced. They are released in the bloodstream, okay? Whatever is happening in the blood, okay? But in case of exocrine glands, whatever is produced, it is released in cavities, in ducts. Is it clear? Yes? Okay. Now, for example, we've got different kinds of endocrine glands. For example, pituitary secretions, okay, thyroid hormone secretions, parathyroid hormone secretions. There's so many hormones, so many glands which produce different types of hormones. Now, in case of endocrine glands, hormones are released. Once the hormones are released in the bloodstream, remember, it reaches their target cells or target tissues. But in target tissues, you need a receptor, okay? So, to see the hormone action, what do we need? We need the receptor. Receptors are very, very important for the action of hormones. So to see the hormone action, you require the receptor. Okay, so the hormones are released in the bloodstream. They reach their target cells. Once they reach their target cells, they bind to their receptor. Okay. Now, let's see what are receptors. We said that hormones, once they are released, they reach their target cells, they have to bind to their respective specific receptor. So receptors are specific for the hormones. Is it clear? Receptors are specific for the hormones. Now, for all the hormones, okay, I'm not talking about the quality of the hormone. You can have different types of hormones, okay? For all types of hormones, the receptors are either protein or glycoprotein. Very, very, very important, okay? So, if I ask you what is the quality of the receptor, you will say it is either protein or glycoprotein. For different kinds of hormones, okay? It doesn't make any difference what type of hormone you are having in your bloodstream. Always the receptors are either protein or glycoprotein. Very, very important, okay? So the receptors are either protein or glycoprotein. Okay, remember, everything in our body, okay, has got a turnover. It is synthesized, it is destroyed. Synthesized, destroyed, okay? It's the same for the receptors. Receptors in our body, they are synthesized, they're broken down. They're synthesized, they are broken down. Is it clear?
Yes.
Yes? Okay. Okay, I see. Sometimes in our body, you've got large amounts of hormone, okay, but your body does not need that much hormone, okay? Or sometimes in our body, we do not have enough hormone, and our body needs the hormone, okay? There should be a regulation. What does it mean, regulation? Regulation means you should not have excess of something or low amounts of something. There should always be a balance, okay, in our body. Now, when, for example, there's a large amounts of hormone, okay, in our body, and our body does not need it, what happens? All the receptors are down-regulated, okay? They go inside. Somehow they hide themselves, okay? So when you do not have the receptor, you cannot see the hormone action. Is it clear? So when there is excess of hormone, what happens? The receptors are down-regulated. The receptors are down-regulated. They either move inside the cell or they're destroyed, okay? Okay, now suppose my body needs the hormone and I do not have enough hormone. What happens? Now the receptors are upregulated, okay? What they do is, whenever there's also a little amounts of hormones are passing, they catch it, okay? So, in case of large amounts of hormone, what happens? The receptors are down-regulated. When you do not have enough hormones, what happens? The receptors are upregulated. The receptors are upregulated. Is it clear? Yes? If you have any questions, just raise your hands, okay?
Do they also become more sensitive to the hormone in upregulation?
We cannot talk about sensitivity as such now. We are talking about the amount, okay? When you have large amounts of hormone or you do not have enough hormone in your body, okay? It can be either upregulated or downregulated, okay? Okay. Now, let's see what types of hormones we have in our body, okay? A group of hormones are circulating hormones, okay? Circulating hormones are all the hormones which they are released in the bloodstream, they travel in the bloodstream, they reach their target cells, okay? So circulating hormones are the hormones which are produced by for example, the gland. They travel in the bloodstream, they reach their target cells, okay? So they are circulating, so they circulate in our body. There are other kinds of hormones, okay? Some hormones, when they are produced, they act on their neighboring cell, okay? For example, hormone is produced over here, it acts on the neighboring cells, okay?
Paracrine.
So they are known as paracrines, very, very important. So what are paracrines? paracrines are hormones which are produced and they act on the neighboring cells. Very important. Okay? Now, there are some hormones, once they are secreted, okay, they act on themselves. Okay, the hormone is produced, they act on themselves. They are known as autocrines. Okay, so we have circulating hormones. Also remember, we call the circulating hormones, in general, we call it endocrines. Okay, so circulating hormones, paracrines, and autocrines. We call the circulating hormone, we call it endocrine. Altogether, we call it endocrine. Some books, if they want to mention about the hormones, okay, even about the paracrines and autocrines, altogether they call it endocrine. But actually, endocrine hormones are circulating hormones. Okay? Endocrine hormones are circulating hormones. Okay, see here. Okay, now, we said circulating hormones or endocrines, right? Okay, these are the circulating hormones. Hormones are produced, they move in the bloodstream, they reach their target cells, they bind to their receptor, specific receptor, and we see the hormone action. Okay, in case of paracrines, see here, the hormone is produced, it acts on the neighboring cell. Okay, they act on the neighboring cell. In case of autocrines, the hormone is produced, it acts on the same hormone, the same cells which have produced the hormones. Okay, now let's see what are different classes of hormones, what are the quality of the hormones, okay? There are different kinds of hormones. Some of the hormones are lipid-soluble hormones, some of them are water-soluble hormones. Now, in case of lipid-soluble hormones and in case of water-soluble hormones, they act differently, okay? The way they bind to the receptor, they work differently. So we are going to see how they work, how the hormones affect, how they bind to the receptor, and how they act or affect the body system. Now, in case of lipid-soluble hormones, for example, we can talk about steroid hormones, thyroid hormones, okay? These two hormones are lipid-soluble hormones. We have water-soluble hormones, they can be like amines, peptides, glycoproteins, proteins, okay? Different kinds of okay, these are the structure of lipid-soluble hormones. Okay? Like for example, we have steroid hormones, or we have, for example, thyroid hormones. Okay? Okay. Now these are water-soluble hormones. As I said, we can have.
Do we have to memorize them?
No. I'll tell you by the end of the lecture what are the things that you have to remember. Okay. I'm emphasizing on important points. Okay, that you should remember for the examination. Okay. Now, let's see what is the general mechanism of hormone action. Okay. Hormones, once they are produced, as we said, they go and bind to their specific receptor, right? What is the quality of the receptor?
Protein or glycoprotein?
Glycoprotein. Okay, the receptors were either protein or glycoprotein. Okay, the hormone receptor complex is formed. Now what will happen? A new molecule is synthesized. Usually we have synthesis of some proteins, enzymes, okay? So a new molecule is synthesized, or sometimes the permeability of the membrane changes. It alters the permeability of the membrane. Molecules, they can move freely out of the cells, okay? Or ions can move freely out of the cells, or they can enter the cells. And it alters the rate of reactions, sometimes because of the hormone receptor complex which is formed. Some reactions are increased, sometimes they are stopped, okay? So it alters the rate of reaction. Okay, so synthesizing a new molecule, it can be a protein or it can be an enzyme, changing the permeability of the membrane and alters the reactions, okay? It alters the chemical reactions which takes part in the body. Hormones on different target cells, they can act differently, okay? For example, when I'm talking about insulin. When insulin reaches the liver cells, it binds to these receptors on liver cells. It stimulates glycogen synthesis. But when insulin reaches the adipocytes, okay, the fat tissues, what happens over there? It stimulates
TG.
TG synthesis, or triglyceride synthesis. So as you can see, it's the same hormone, it can act differently, okay, depending upon the target cells, okay? Whether it's acting on liver cells or it's acting on the adipose tissues. Okay. First, I'm going to start with lipid soluble hormones. Let's see how lipid soluble hormones act. Okay, now when lipid soluble hormones, okay, they reach their target cells, remember, the receptor for lipid soluble hormones, is either in the cytoplasm or it is in the nucleus. Okay, very, very important. So, in case of lipid soluble hormones, the receptors are either in the cytoplasm or in the nucleus. In case of steroid hormones, the hormone receptor complex is formed in the cytoplasm. So the receptor is in cytoplasm. Is it clear? Once again, I repeat. In case of steroid hormones, the hormone receptor complex is formed in the cytoplasm. So the receptor for the lipid, the receptor for steroid hormones is present in cytoplasm. Very, very important. In case of thyroid hormones, the receptor for thyroid hormones are present in the nucleus. So, the hormone receptor complex for thyroid hormones, where does it happen? It happens
Cytoplasm.
in the nucleus. For thyroid hormones,
Thyroid?
in the nucleus. Is it clear?
Yes.
So, depending upon where the receptor is, the hormone receptor complex is formed. I repeat again. So suppose I have a steroid hormone. Where is the receptor for steroid hormone?
Cytoplasm.
In cytoplasm. The receptor for thyroid hormones is present in the
Nucleus.
nucleus. Very important. So the hormone receptor complex for steroid hormones happens in cytoplasm. The hormone receptor complex for thyroid hormones happens in the nucleus. Is it clear?
Yes.
Fine. Okay, I think I'm going to show it to you on the board. Okay, the same structure. Okay, what you see over there. Okay, suppose this is the cell. Suppose this is the cell surface. Suppose this is the cell surface, this is the nucleus. Okay? Now, the hormone is coming. Okay, we've got the receptor, okay, this is the receptor which is present in the cytoplasm. This is the receptor which is present in the nucleus. Okay? Now, the hormone is coming. Suppose the hormone is a steroid hormone. Okay, the steroid hormone is coming. It enters the cell. It goes and binds to its receptor. Where?
Yeah, the
In
cytoplasm.
So the hormone receptor complex is formed. Okay? Now, this complex now enters the nucleus. Where does it go? It goes on the surface of DNA. Okay? There is a portion on DNA which is known as HR E. Hormone response element. Hormone response element. So we've got hormone response element. Hormone response element. So what happens? This complex goes and binds to a portion of DNA which is known as HRE. So this portion is known as HRE, hormone response element. So we have synthesis of mRNA and synthesis of a new protein. Is it clear? Okay. Now, suppose my hormone is a thyroid hormone. What happens? The thyroid hormone comes, it enters the cytoplasm, it moves inside, okay, it goes, it binds to this receptor where? In the nucleus. Okay, now what happens? This complex goes and binds to HRE, hormone response element. Okay, what happens? Synthesis of mRNA, synthesis of new protein. Is it clear? Okay. So I repeat again. Suppose my hormone is a steroid hormone. Okay, what happens? The steroid hormone enters the cell, goes in the cytoplasm, it finds its receptor, hormone receptor complex is formed. Where does this complex go? In the nucleus. Where does it bind? HRE, hormone response element. Then we have synthesis of mRNA, synthesis of a new protein. Now this protein can be, for example, an enzyme. Okay? Okay. Now, the thyroid hormone is coming. The thyroid hormone, it goes through the cytoplasm, it goes inside the nucleus. It goes, it finds its receptor, okay? It binds this receptor in the nucleus. So hormone receptor complex is formed. Now, where does this complex go? It goes and binds to HRE, okay? Hormone response element. So you have synthesis of a new protein. Is it clear? Yes? Okay. It was easy, right? Yes, very easy. Okay. Next, let's go to water-soluble hormones. Okay. Now listen, in case of water-soluble hormones, okay, water-soluble hormones, when we talk about this is suppose the cell. Cell is made of what? Lipid. Double layer, yes. Right? Okay. So the hormone cannot pass through this. Okay? The hormones, the water-soluble hormones, they cannot pass through the cell membrane. Why? Because they're water-soluble. Okay? They cannot pass through the membrane. So what do I need now? I need a receptor which is present on the cell surface. Okay? So, in case of water-soluble hormones, where are the receptors?
On the cell surface.
They're on the cell surface. Okay? Is it clear? Okay. So, the hormone receptor complex is formed on the cell surface. Okay. Now, the hormone has got some message. The message has to go inside the cell. How does it go inside the cell? I need second messengers. Okay? So, in case of water-soluble hormones, what do I have? I have the receptors on the cell surface. Okay? So the receptors are on the cell surface. Why? Because my hormone cannot go inside. Because it's water-soluble. It cannot pass through the cell membrane. So hormone receptor complex is formed where? On the cell surface. Now, this information has to go inside. Okay, how does it go? With the help of second messengers. With the help of second messengers. What are these messengers? For example, cyclic AMP, cyclic GMP, calcium ions, phosphatidylinositol, and tyrosine kinase. Which will see this together.
Doctor,
is it clear?
Is adenylate cyclase a second messenger?
Yes, now I'm going to explain. Okay, I'm going to explain. Okay, if you don't have any questions, okay, I'll continue.
Okay.
No questions?
No.
Oh, okay. Should I wipe this?
Yes, please.
Yes? Okay. Okay. Now, okay, this is my cell surface. Okay, this is my cell surface, okay? And this is my receptor. Where is it present on the cell surface, okay? Okay, now listen carefully. The receptors are either stimulatory or inhibitory. Okay? The receptors which are present on the cell surface are either stimulatory or they are inhibitory. Is it clear?
Yes.
Okay. Stimulator means
They start
stimulates.
stimulation.
Inhibitory means
Inhibitory.
inhibits. Okay? Now, so the receptors are either stimulatory or inhibitory. If the receptor is stimulatory, the hormone which comes and binds to it is stimulatory. Okay? So the hormone which comes and binds, okay, suppose the hormone is coming. The hormone is stimulatory. Okay? Okay. If the receptor is inhibitory, the hormone which comes is inhibitory. Okay, so the hormone is coming. Okay? Okay. Now, the hormone comes, it binds to the stimulatory receptor. So hormone receptor complex is formed. Hormone receptor complex is formed. Okay, suppose this one comes. The hormone receptor complex is formed. Now, over here, dropping everything, I'm sorry. Okay, over here, okay, there is a protein which is known as a G protein. G protein. G protein is, for example, in this case is GS. It is made of 3 subunits, alpha S, beta, gamma. Okay? For this also I've got the G protein. What is the G protein? GI. Right? Okay, it's GI. What is it made of?
Alpha.
Alpha I, beta, gamma. Okay? So, I have a G protein, okay, which is present where the hormone receptor complex is formed. This G protein is made of 3 subunits. 3 subunits means what? 1 chain, 2 chain, 3 chains, okay? 3 subunits. It is made of 3 chains. It's alpha S, beta, gamma. In case of GI, it is alpha I, beta, gamma. Alpha I, beta, gamma. Is it clear?
Yes.
Okay. Now, let's see what happens. When the hormone receptor complex is formed, these 3 subunits, they separate. Alpha S is separated, okay? Alpha S, beta, gamma. Okay? So when this complex is formed, this is broken down into what? Alpha S, beta, gamma. When this complex is formed, this is broken down into what? Into what? Beta, gamma, and alpha I. Okay? See, this subunit beta, gamma is same for both of them. So the quality is same. Okay? Now, what happens? Alpha S stimulates an enzyme which is known as adenylate cyclase. Adenylate cyclase. So there's an enzyme which is known as adenylate cyclase. What does adenylate cyclase do? Adenylate cyclase
ATP
converts ATP
into AMP.
into cyclic AMP. So alpha S stimulates activity of adenylate cyclase. Okay? So what happens? Large amounts of cyclic AMPs.
Produced.
What does alpha I do? Alpha I, it inhibits the activity of adenylate cyclase. So what happens? The level of cyclic AMP is dropped. Okay, so I repeat once again. What did we say? We said that when hormone receptor complex is formed, what happens? A G protein is activated. Okay? G protein is made of what? Alpha S beta gamma. Okay? Now, so stimulatory hormone comes, binds to stimulatory receptor. This protein is activated. This protein is made of 3 subunits: alpha S, beta, gamma. Once this complex is formed, this separate, beta gamma goes away, alpha S is released. What does alpha S do? It activates adenylate cyclase. That's got a positive effect on adenylate cyclase. So ATP is converted into cyclic AMP. Is it clear?
Yes.
Now, if the inhibitory hormone comes, it binds to the inhibitory receptor. What happens? GI is activated, alpha I is separated, okay? Beta gamma goes away. Alpha I inhibits the activity of adenylate cyclase. So cyclic AMP is decreased. Is it clear? Okay. Is there any questions here? No? Okay. Please pay attention, okay, carefully now. Now, cyclic AMP, what does cyclic AMP do? Cyclic AMP acts on, it causes the activation of a protein kinase. Okay? So, because of cyclic AMP, inactive protein kinase is converted into active protein kinase. Okay? So, an enzyme is activated. Okay? A protein kinase is activated. Remember, kinases phosphorylate. What do kinases do?
Phosphorylate.
Phosphorylate. Okay. So active protein kinase acts on, it converts inactive phosphorylase kinase into active phosphorylase kinase. So active protein kinase converts inactive phosphorylase kinase into active phosphorylase kinase. What has it done? It has phosphorylated. It has phosphorylated the phosphorylase kinase. Now, active phosphorylase kinase converts inactive phosphorylase into active phosphorylase. Okay? I'll explain it, okay? Okay, see here. What happened? We said that hormone receptor complex was formed, alpha S was separated, alpha S acted on adenylate cyclase, and what happened? ATP was converted into cyclic AMP. Okay, what does cyclic AMP do? It activates the protein, okay? So, an inactive protein kinase is converted into active protein kinase. Active protein kinase acts on inactive phosphorylase kinase. It converts it into active phosphorylase kinase. What does active phosphorylase kinase do? It converts inactive phosphorylase into active phosphorylase. What does phosphorylase do now? Phosphorylase acts on glycogen. It starts breaking down glycogen. Okay, so what happens? Gradually the level of sugar in the blood rises. Okay, so what does phosphorylase do? Phosphorylase acts breaks down glycogen. Okay? So what happens? The level of sugar, so glycogen is broken down and glucose is released. So the level of sugar is raised. The level of sugar is raised. Is it clear? Yes? Okay. Now, there are some okay. There are some compounds, okay? There are some compounds which are known as xanthine compounds. Xanthine compounds. So there are some compounds which are known as xanthine compounds. Let's take for example xanthine compounds, okay? For example, you drink tea. What is there in the tea?
Caffeine.
Theophylline. Theophylline. Okay, you drink coffee. What's there in the coffee?
Caffeine.
Caffeine. Caffeine. You drink cocoa. What's there in cocoa?
Caffeine as well.
Theobromine. Okay, these are all xanthine compounds. Okay? For example, tea, coffee, cocoa. Why do you drink tea? Why do you drink coffee? Yeah, you're tired, okay? You want to study, okay? So you feel sleepy. So what you do, you drink coffee, you feel fresh. Isn't it? Yes or no?
Yes.
Yes. Xanthine compounds, what do? Xanthine compounds like coffee, tea, cocoa, theophylline, theobromine, caffeine. What do? They activate adenylate cyclase. They activate adenylate cyclase. So xanthine compounds have got a positive effect on the activity of adenylate cyclase. Okay, now you tell me what happens. Adenylate cyclase is activated. What is raised? Cyclase. What happens? Inactive protein kinase.
Active protein kinase.
Kinase. Inactive phosphorylase kinase.
Phosphorylase.
Active phosphorylase kinase. Inactive phosphorylase is converted
To active.
phosphorylase. What happens now?
Glycogen
Glycogen
into
is broken
glucose.
down. What is increased? Glucose. That is the reason you feel fresh. Okay? Why? You take coffee, you take tea. Okay? What happens? These xanthine compounds, what do? These xanthine compounds, they act on the activity of adenylate cyclase. So adenylate cyclase is increased, the level of cyclic AMP is increased. Therefore, what happens? Glycogen is broken down. So the level of sugar is raised in your blood. That is the reason you feel fresh. When you take tea, you feel fresh, you feel good. Is it clear?
The same mechanism of glycogen?
Sorry?
Glycogen? The same of the mechanism of glycogen?
I can't understand.
Glycogen hormones, the same mechanism of it. Rise the blood.
The level of yes. Okay. Is it clear? It's interesting, isn't it?
Yeah.
Yeah, very interesting. Okay. There's an enzyme which is known as phosphodiesterase, very important, okay? Phosphodiesterase. Remember, phosphodiesterase inhibits, phosphodiesterase inhibits the activity of adenylate cyclase. It inhibits the activity of adenylate cyclase. It actually, you know what phosphodiesterase somehow it regulates. You know, if too much cyclic AMP is produced, phosphodiesterase inhibits. Okay, remember, it's very important. So if I ask you which of the following inhibits the activity of adenylate cyclase, what will you say?
Phosphodiesterase.
Phosphodiesterase. Which of the following increases the activity of adenylate cyclase?
Xanthine compounds.
Xanthine compounds. Xanthine compounds. Is it clear?
Yes.
So phosphodiesterase inhibits the activity of adenylate cyclase. So it regulates. It has got a regulatory effect. It has got a regulatory effect. Is it clear? Any questions so far?
No.
No? Should I repeat everything again?
No, we understand.
Understood?
Yeah.
Yes.
Yes.
Yes. Oh, I'll say it quickly, okay?
Okay.
Just pay attention. So we said the hormone which is coming, it can be either a stimulatory hormone or
Inhibitory hormone.
If the stimulatory hormone comes, it binds to the stimulatory receptor, a G protein is activated. What is the G protein? GS.
GS.
What is GS made of? Alpha S,
Alpha S,
beta gamma. Alpha S is
Separates
separated.
from beta.
What does alpha S do? It activates
Adenine
adenine
cyclase.
cyclase. So ATP is converted into cyclic ADP. Then we've got series of reactions. Finally, phosphorylase is activated. What does phosphorylase do?
Break down.
Breaks down
glycogen.
glycogen. Glucose is increased. What does xanthine compounds do? They have got a positive effect on the activity of
Stimulate adenine
adenine
cyclase.
cyclase. Is it clear? What does phosphodiesterase do?
Inhibit.
It inhibits the activity of adenylate cyclase. Is it clear? Any questions?
Nope.
Okay, great. Okay. Okay, now, remember, when, for example, hormone binds to its receptor, okay, about 100 G proteins are activated, okay, this amplification, okay, so like one process causes a huge thing to happen, okay, so when hormone receptor complex is formed, so many G proteins are activated, about 100 G proteins. Thousands of cyclic AMPs produced. Okay, so you can see that actually so much. Okay, it's so huge, so big. Okay, so everything happens so quickly in our body. That is the reason, for example, when you're tired, when you take, for example, coffee, very quickly you feel fresh. Okay, this happens so quickly in our body. Okay. Okay. Next is cholera toxin. Okay, have you heard about cholera? You know what's
Yes.
cholera?
Yes.
Cholera, or we call it vabo. Okay, cholera, when people are affected with cholera, what happens all the time, they start, they have diarrhea. You know this diarrhea?
Yes.
All the time they run to the toilet.
Mhm.
Okay, so they have diarrhea. It's like watery, okay? It's too much, it's so much electrolytes are gone out of the body that after some time the person will die, okay? Because the electrolyte imbalance is very, very dangerous in our body. Okay, if the electrolytes balance is, anything happens with the balance, that the person, dies. It's so important. Okay, like for example, dehydration. We say dehydration. Dehydration is very important. Okay, because you're using too many ions from your body, and it's very, very dangerous. Is it clear? Okay. Now let's see what happens in cholera. The cholera produces a toxin which is known as cholera toxin. Okay, this toxin, what does it do? It locks G protein in its active form. Okay, so G protein is activated. Remember G protein? Alpha S, beta gamma. Yes. Okay. So it locks it in an active form. Then what happens? When it is locked in its active form, large amounts of cyclic AMP is produced. Now what happens? It actively transports chloride, sodium, and water, okay, into the lumen. Okay, so what happens? G protein is locked in its active form. Then large amounts of chloride, sodium, and water, they are thrown in the lumen. So what happens? They come out of the body. After some time, what happens? There's an imbalance in the electrolytes in the body, and the person can die. It is very dangerous. So if I ask you, what does cholera toxin do? What will you say? It locks G protein in its active form. It locks G protein in its active form. So what happens? Large amounts of chloride, sodium, and water are thrown in the lumen. Is it clear? Yes? Okay. Okay, now next is, okay, phosphatidyl inositol diphosphate. Let's see what is this one, okay? Should I write this?
Yes.
Next is phosphatidylinositol. Phosphatidylinositol diphosphate. First, let's see what is the structure of phosphatidylinositol diphosphate. Okay, suppose I have glycerol. You remember glycerol?
Yes.
Yes, glycerol. This was glycerol.
Echo.
No,
3 carbons, 3 OH. Remember? Okay. This is glycerol. So what I'm going to do to glycerol? I'm going to add 1 fatty acid. Fatty acid. Okay, I'm very sorry. I'm dropping everything today. And it's white. Okay, and I'm adding a phosphate. Okay? Okay? This is phosphatidic acid. Is it clear? Again, glycerol, fatty acid, phosphate. Phosphatidic acid. To phosphatidic acid, I'm going to add inositol. This is inositol. Okay? This inositol by itself, okay, suppose this is inositol. Inositol has got a large, all OH on the structure. It's like this. This is inositol. It's not a sugar because it doesn't have oxygen over here. Okay? It's not a sugar. This is inositol. Okay? So on the structure of inositol, I'm going to put 2 phosphates. 1 phosphate, for example, over here, and 1 phosphate over here. So this is inositol diphosphate, isn't it?
Yes.
Inositol diphosphate with 2 phosphates.
Yes.
Okay. I'm going to, from here, this is phosphatidic acid. I'm going to add this over here. So I'm going to add inositol diphosphate. This is inositol with 1 phosphate and 2 phosphates. Is it clear?
Yes.
Yes? Okay. So, now what is the structure? This was phosphatidic acid. This is what? Inositol diphosphate. So, phosphatidyl inositol diphosphate. Phosphatidyl inositol diphosphate. Did you understand the structure?
Yes.
Yes? Okay. Now, remember, when hormone receptor complex is formed, what happens? This structure, phosphatidyl inositol diphosphate, is cut from here. Okay? Now, inositol has got how many phosphates? 3 phosphates. Okay? So it's inositol triphosphate, IP3. Right?
Yes.
What is left over here? A glycerol and 2 fatty acids, diacetyl glycerol, diacetyl glycerol. Okay, so diacetyl glycerol. We call it fatty acid and acyl, right? So 2 fatty acids and glycerol, diacetyl glycerol, or DAG. Yes?
Yes.
Did you all understand?
Yes.
Okay, I'll repeat again. What did I have? My next secondary messenger is phosphatidyl inositol diphosphate. What is phosphatidyl inositol diphosphate? Okay. I have glycerol, 2 fatty acids, and 1 phosphate. This is phosphatidic acid. To phosphatidic acid, I'm going to add 1 inositol diphosphate. So it is phosphatidylinositol plus diacetyl, sorry, diphosphoinositol, okay? So it is phosphatidylinositol diphosphate. So this is phosphatidylinositol diphosphate. When hormone receptor complex is formed, this is cut from here, okay? So what is separated? Glycerol 2-fatty acid, which is known as DAG, DAG, diacylglycerol, and inositol 3-phosphate. Family? Yes? Okay. Okay, now it's easy. See here. Hormone receptor complex is formed, okay? What is separated? Phosphatidylinositol diphosphate. Can you see PIP2? Yes. And what is separated? DAG. Okay. Now IP3 or inositol 3-phosphate here. Inositol 3-phosphate. It binds to soft endoplasmic reticulum. It binds to soft endoplasmic reticulum. What is released? Calcium is released. Okay? So calcium is released. Now this calcium goes and binds to a molecule, okay, in the structure of enzyme. See here. This is an enzyme. Suppose this is an enzyme. On enzymes, sometimes there's a portion which is known as calmodulin. The calcium which are released, they go and bind to calmodulin. Okay, what happens when they bind to calmodulin? Now the enzyme becomes active. Okay, the enzyme becomes active. So inactive protein kinase, it is converted into active protein kinase. Okay, so I'll repeat again. Hormone receptor complex is formed. Okay, what happens? Phosphatidylinositol diphosphate is broken down into what? IP3 or inositol 3-phosphate, okay, and DAG. What does IP3 do? Inositol 3-phosphate goes and binds to soft endoplasmic reticulum. What is released? Calcium. Calcium is released. Calcium goes and binds to calmodulin. What is calmodulin? Calmodulin is the portion on the enzyme. So inactive protein kinase is converted into active protein kinase. What do kinases do? They phosphorylate. Is it clear?
Yes.
Okay. Let's see what is the fate of DAG. Okay, here I have DAG. Again, DAG goes and acts on a kinase C. It activates kinase C. See here, again, the protein is, with the help of calcium, the protein is phosphorylated. So that also goes for the activation of protein kinase. Okay? It activates a protein kinase. So I repeat again. We have phosphatidylinositol diphosphate. This is phosphatidylinositol diphosphate. Hormone receptor complex is formed. This is cut from here. DAG IP3. What does IP3 do? It goes and binds to soft endoplasmic reticulum, right? What is released? Calcium. Where do calcium go and bind to? To calmodulin. Then what happens? Inactive protein kinase is converted into active protein kinase. Okay, what does DAG do? DAG goes and activates protein kinase. Yes. Kinase C is a protein kinase C. Okay, it is activated. So kinases, what do kinases do? They phosphorylate. Easy? Yes. Okay. Okay, this is calmodulin. Okay, it goes and binds. Calcium goes and binds to calmodulin. Okay, let's go to insulin receptor. Okay, this is insulin receptor. Insulin receptor is made of 4 subunits. Okay, 4 subunits. 4 chains, 2 alpha, 2 beta. Okay? So 2 alpha, 2 beta. The 2 beta subunits, they pass, this is the membrane, they pass through the membrane. Okay? So the 2 beta subunits, they pass through the membrane. The beta subunits have got the protein kinase, they have got tyrosine kinase activity. The beta chains have got tyrosine kinase activity. So whenever there is any tyrosine, what they do, they phosphorylate tyrosines. Understood? So the beta subunits have got tyrosine kinase activity. What they do, all the tyrosines which are there on the beta subunits, they are phosphorylated. Okay? Now see. Okay. See here. Okay. This is the insulin receptor. What is there? Right on. Insulin is coming. Okay, just see. Insulin comes. It binds to its receptor. Now, what did I say? I said the beta subunits have got tyrosine kinase activity. Now see what happens. See, it is phosphorylated. So the tyrosine is phosphorylated. Now see what happens. Series of reactions happen. So many proteins are synthesized. Can you see? The proteins are synthesized. Okay, now finally, the glucose transporter is synthesized. Okay, now this glucose transporter goes, opens a space. See? Now what happens? See, glucose is coming inside. So interesting, no? Yes, I love this slide. Okay, I think it's lovely. See here, see how glucose are coming inside? Yes, okay. Okay, so again I repeat. Let's go back. We said that we've got insulin receptor. Insulin receptor is made of how many subunits? 4 subunits. 2 alpha, 2 beta. The beta subunits have got tyrosine kinase activity. Tyrosine kinase activity. Okay, see here. Okay. The insulin is coming, it binds to the beta subunit, to alpha subunit. What happens to the beta subunit?
Activates
It is
phosphorylated.
It is phosphorylated. Now, many proteins are synthesized. Finally, a glucose transporter is synthesized. What does the glucose transporter do? It goes, it opens a space in the cell membrane. Now, glucose is entering. Glucose comes inside. Okay? Okay. Now, next is hormonal interactions. Now, sometimes we got 2 hormones, okay? 2 hormones. Sometimes, let's see how these 2 hormones can work together. Sometimes they're effective permissive, sometimes it is synergistic, sometimes it is antagonistic. Let's see what does it mean. Okay, permissive means the second hormone threatens the effect of the first hormone. For example, thyroid threatens the effect of epinephrine. Okay, so one hormone threatens the effect of the second hormone, so they work together better, isn't it? Okay, next, synergistic effect. 2 hormones work together for greater effect, for for higher effect, we can say. For example, estrogen and LH. Okay, now we need the level of estrogen. LH rises, and estrogen together. It goes for ovulation. So 2 hormones, they act together for a greater effect. This is known as synergistic effect. Next is antagonistic effect. That means 2 hormones act opposite each other. For example, insulin causes glycogen formation, but glucagon causes glycogen breakdown. So they act opposite direction. Okay, so we can have permissive, synergistic, antagonistic. So in case of permissive, second hormone strengthens the effect of the first hormone. Synergistic means two hormones work for a greater effect. Antagonistic means two hormones, they act in opposite directions. Is it clear? Okay, great. Okay, now, okay. Remember, when hormones are produced in our body, when a molecule is synthesized in our body, when a molecule is broken down in our body, for all the cases, whatever is happening in our body, there should be a regulation. You know what is regulation? You should not have large amounts of hormone is produced or low amounts of hormone is produced. Both of them can cause problems in our body. Large amounts of one molecule is produced or low amounts of one molecule is produced, you might become sick, okay? So there should always be a regulation, okay? Now in case of hormones, okay, for example, if I say, for example, in case of thyroid hormones, okay? Now, we have got, for example, TRH at the hypothalamus level, then we've got synthesis of TSH. Okay, now we discuss this later on, okay, not today. TSH, for example, at the level of hypophysis, okay, or pituitary gland. Next we have the synthesis of T3 and T4. Now, if large amounts of T3 and T4 is there, they can inhibit the production of TSH at the pituitary level or TRH at the hypothalamus level. So there should always be a regulation. Regulation is very, very important, okay? Regulation is very, very important. If you do not have enough TSH, okay, TRH can have a positive effect on the production of TSH. TSH can have a positive effect on the production of T3 and T4 at the thyroid gland. So we need a regulation, okay? Now, in case of this, I can say it has got a positive effect, but this is a negative feedback, okay? Negative feedback which we get when large amounts of hormones are produced. Okay guys, if you do not have any questions, okay, I'll finish with hormone action. We can take a break, say for example for half an hour, we'll meet again.
Okay.
Okay?
Thank you.